Welcome again to another section on spectroscopic technique. Today we are going to be looking at UV spectroscopy. What is UV spectroscopy? We are going to be looking at what is UV. We are going to be looking at UV spectroscopy by first talking about what it has to do with. So we are going to be talking about which regions of the electromagnetic spectrum are we considering. We're also going to be looking at some of the things that characterize UV spectroscopy. At the same time, maybe do an intro into electronic transitions. Now, what is UV spectroscopy? UV spectroscopy is a spectroscopic technique that is majorly used in elucidating the structure of compounds that have a conjugated system. So, in using UV spectroscopy, most times it always has to do with compounds that have conjugation within them. What do I mean by, so I could say that UV spectroscopy deals with compounds with conjugation. Be active and a compound can be UV inactive, in the sense that you can have a compound that can absorb that can be measured, or that can be measured using UV spectroscopy. I can have a compound that you can't measure with using UV spectroscopy, depending on the presence of conjugation. So what is conjugation? Or when do we have a conjugated system? Conjugated system has to do with double bonds. When you have two or more double bonds. But the way the double bonds will be arranged differs for different systems. The way it's arranged in a conjugated system is different from the way it's arranged in a conjugated system, and the way it's arranged in an isolated system. To make a quick summary, in conjugated system, two double bonds are separated by a single bond. In completed system, the two double bonds are separated by no single bond. And in an isolated system, the two double bonds are separated by two or more single bonds. I'm going to give you an example on each of them. For example, we have CH3, CH double bond, CH. We have single bond CH double bond CH2. Now, in this particular structure that is drawn on the board, this is a double bond, this also is a double bond. The two of them are separated by a single bond. That makes it a conjugated double bond. In a conjugated double bond, we have something like this. We have CH3, CH double bond C double bond C H2. Now, in a compound as this, you can see that these two double bonds are not separated by any single bond, and that makes them a commutated system. For isolated, whereby I said when you have two or more single bonds separating two double bonds, then you have. So an example is when I have CH2 double bond CH single bond CH2 single bond CH double bond CH2. Now, in this particular example, we have two single bonds separating two double bonds. So this is an example of an isolated system. So, like I said, the focus of UV spectroscopy is to study or to measure conjugated system. So, like I said, any structure that have or any compound that have a system like this, whereby two double bonds are separated by a single bond, can be said to have conjugation, and that's the focus of UV spectroscopy. Now, what regions of the electromagnetic spectrum are we using for under UV spectroscopy? We majorly in UV spectroscopy are concerned with two major regions, which is the ultraviolet region and the visible light. the visible region. Now, for the ultraviolet region, this is between 200 nanometer to 400 nanometer, while for visible region, it starts from, let's say, 400 nanometer to 700 nanometer. Now, these are two regions that we consider in UV spectroscopy. So, any compound that can absorb light in this region, we can say it is UV active. But any light that could not absorb light in this particular region, we can say it is UV inactive. Now, the next thing to talk about is what characterizes UV at some particular characteristics of absorptions under the UV spectroscopy, which is two things. So, in measuring absorption using UV spectroscopy, two things are very important, which is intensity and wavelength. For any absorption under UV, under UV spectroscopy, you must be able to tell us about the wavelength of absorption, at the same time the intensity of absorption. And from the um, former lessons that we have done on wavelength and wave number, we have talked about the units for wavelength, which is nanometer. But the quantity for measurement of intensity is what we term molar absorptivity, which is denoted by what? By epsilon. So molar absorptivity is a measure of intensity, and the higher the molar absorptivity, the higher the intensity of absorption. So we must know that these two quantities are very important quantities that characterize UV absorption. We must be able to know the wavelength of absorption in the when you have your UV spectroscopy. At the same time, you must be able to tell us about the intensity of absorption. Now, for absorptions under UV spectroscopy, an absorption can be symmetry forbidden. Also, it can also be symmetry allowed, depending on the value of molar absorptivity. When the when the molar absorptivity is less than 1000, then there is tendency that the absorption will be symmetry forbidden. And when it is more than, let's say, 10,000, when it is more than 10,000, then it is symmetry allowed. And partially also, when it is in between 1,000 and 10,000, we can say that it is partially symmetry allowed. And these are some of the things that we have to take note in terms of absorption under UV spectroscopy. We must take note of the intensity of absorption and the wavelength of absorption. These two quantities are very important things to also denote. And I've said that the measure of intensity is molar absorptivity, which I said is denoted by what? By epsilon. The greater the molar absorptivity, the higher the intensity. At the same time, we must not try to mix up the intensity of absorption and probably energy of the absorbed light. Those two things are different things. Intensity is not the same thing as energy. We can recollect that in the introductory lesson for spectroscopic technique, we mentioned the fact that energy equals to Hf, which is also equals to Hc over lambda. So that implies that the energy of absorbed light is directly proportional to frequency and is inversely proportional to wavelength. That is very so. Energy of absorbed light is not the same thing as molar absorptivity. And these are some of the things that I would say we have to do as touching UV spectroscopy. In the next lesson, we are going to be looking at another very important aspect of UV spectroscopy, which is Beer-Lambert law. and we're going to see the relationship between absorbance and concentration. At the same time, we're going to see the relationship between absorbance, which is a unit, a quantity for measuring absorption of a particular light ray. We are going to be looking at that in the next lesson. So, in summary, we've talked about UV spectroscopy, what it has to do with the regions of the electromagnetic spectrum that we focus under the UV spectroscopy, and we're going to look at two particular quantities that characterize UV absorption. So I think at this point we can stop. I hope to drop some other videos that for the continuation of this particular lesson. I also want to encourage you to still continue to watch, learn. You can share, you can like, and at the same time do well to subscribe. Thank you.